Hello, everybody. My name is Roman. I'm going to talk about project Lilliput, also known as compressed object headers. So I'm starting with a little overview, then I'm going to talk about what we call Lilliput 1, what we've done so far, and want to dive deep into more about what we call Lilliput 2, in particular about tiny class pointers and compact identity hash code. I've talked about this Lilliput project last year. I'm trying to not repeat myself too much and talk about other things. So let's start with an overview, and instead of making a long motivational talk, I'm going to give some demos here. All right. Can you all see that? All right. I made a little program. The goal is to demonstrate the size of objects in the Java heap. So what I do here is I create a bunch of objects and I take the identity hash code out of it. The reason why I'm doing this is there is a little flag in the JVM that allows me to, instead of returning a real identity hash code, just give me the address of the object. I'm going to abuse this and stick that in an array, and then I'm going to show the addresses of these objects. So, and the object that I'm creating is just this primitive foo class that there's nothing in it. So let's compile that and run it. So I'm passing this hash code equals 4 option here, which makes the JVM behave incorrectly because the address of an object is not a correct identity hash code. And what you can see here is that the objects are laid out linearly in the heap with a distance of 16 bytes, even though there's nothing inside these objects. So what's those 16 bytes? It's basically 12 bytes of metadata. That is, in fact, it's 8 bytes of the so-called mark word and 4 more bytes of the class pointer there. And then there's 4 bytes of a alignment gap, basically, because objects on the Java heap are aligned by 8 bytes. So I can demonstrate this alignment gap by adding a field here. Let's just add an int field that takes 4 bytes, compile that again, and run it again, and it still has the same distance of 16 bytes per object. So it sticks this int field into this alignment gap. I can add another field here and say, let's just call it x. And this makes the whole thing a bit larger and take 24 bytes instead of 16 bytes. Because now it needs another word and for accommodating this new field. So let's try the same thing with Lilliput. We can actually try the same with arrays, because arrays are a little bit different. So let's do this. I'm allocating empty int arrays here. And we see with this, we are still getting the 16-byte usage of this empty array. So what's the difference between arrays and instances is that the array also stores the array length. In this case, it sticks the array length in this 4-byte gap there. If we just add a single element to this array, this won't be enough anymore. And it's going to this 24 bytes object layout. Okay, let's try to run the same thing with Lilliput just for fun. So I'm going back to the instances again with empty objects, compile it again, and then run it with Lilliput. I have an alias here to a Lilliput build. Otherwise, the same thing. And now we can see this primitive empty object takes only 8 bytes because we have basically merged the class pointer up into the other metadata, and this only takes 8 bytes now. And similar it goes for when I try this with arrays. But let's try another thing here. Let's try to add a field. So this essentially has cut the memory usage of this application in half. You noticed that probably. But it's an extreme case. It's very small objects, and real cases would probably not do this. But let's try this with another field, and lo and behold, it's still only 8 bytes. Why is that? That's because I lied to you. The header only takes 4 bytes. What you see here is what we call Lilliput 2. It compresses the object header down to just 4 bytes. We can try the same now with arrays. So seeing that we have 4 bytes, 4 bytes of object header, we are able to stick the array length in the first 8 bytes too. Yeah, this doesn't compile, sorry. Stupid me. The reason why I need to compile this instead of running it basically using the Java launcher is that because I'm basically breaking identity hash code here by adding this flag, it also breaks the Java C compiler because it's not correct. But it's good enough for showing off. So yeah, the array length is in the first 8 bytes too, so we can fit the smallest kind of array in this single word basically. Yeah, making this a little bit larger means that we take up another word of objects, so this is quite expected by this point. Right, so we back to 16 bytes per object. Okay, enough of this demo stuff. Let's go back to the presentation. Okay. Let's see what goes on under the hood. So first of all, what's in it? The current way objects are laid out is basically what I just described in the demo. Is we have a header, or we call it a mark word. It's taking up the first 8 bytes, which is what the first pink block here is showing. And then we have another 4 bytes of class pointers, and after that the fields or array elements can line up. For arrays, we also have another field that holds the array length. With Lilliput 1, what we did there is we shrink the object header into the first 8 bytes, and then everything else, the fields and the array elements line up after that. And this is zooming into the first basically 12 bytes of the current JVM state. What we see here is the header and the class pointer. And yeah, and going in detail, those are, each letter here or each dot here is basically a bit in the object header. And the meaning of this is going from right to left is basically we have 2 what we call log bits or tag bits. Then we have an unused bit there. We have 4 H bits for the GC H. Then we have another unused bit there. This is historical. The unused bit, the first unused bit used to be the biased locking bit. Then we have 31 bit that holds the identity hash code of objects. And then we have a bunch of unused bit at the top of it. And in the next 4 bytes, we basically store the compressed class pointer. This is taking up 32 bits currently. The insight that we have in Lilliput is, one of the basic insights is that most objects never get identity hash code and most objects never get logged. So we are allocating a lot of bits just there for supporting all this stuff, even though most objects never even use this. But there's more than this. The mark word, the first 8 bytes of the object, they can be overwritten for special purposes, and the tag bits indicate what is in this mark word. And there's 3 different, actually 4 different states there. The default, the normal state is the tag bit 01, which just means that it's the usual mark word that we see here. And then we have the 3 special cases, which is stack locking. In the case of stack locking, actually in all those cases, the upper bits there are interpreted as a pointer. And in the case of stack locking, it's a pointer to the stack location that holds the lock on this object. It can also be a pointer to an object monitor that's somewhere on this C heap, or it can be a pointer to the forwarding object in the case of GC forwarding. And here is what it looks like in Lilliput 1. So we rearranged a bunch of those bits, so the lowest 2 bits are still the same, still the tag bits or log bits. Then we have used one of those unused bits to indicate a self-forwarded object that is for the GC forwarding. The 4 bits for the GCH remain the same. We reserved 4 bits for Valhalla here because we talked to the Valhalla guys. They told us that they might use 4 bits there, for example, to support the larval object state. And then we still have the 31 bits for the identity hash code, and in the upper registers we have like 22 bits to show the class pointer. And we have a big problem right here because in the current JVM the class pointer is in the words 8 to 12, and it's basically always stays there and never goes away. It's basically guaranteed to be accessible, and it's immutable too. We merged it to the object header in the mark word, and the problem is how to not lose this class pointer when one of the JVM features override the mark word. We must not even temporarily lose this class pointer. We always need to be able to recover from that. So this is one of the major challenges in Lilliput. And the way we address this, I talked about this last year, so I don't go into details here, but want to cover it quickly. So one thing we did is implement lightweight locking, which basically is a new implementation that replaces the current stack locking in the JVM. It's actually already in JDK since JDK 21. It's off by default in 21. But it will be on by default since JDK 23, which is about to go on real soon. I talked about this last year, so if you want to see the details, then you go to YouTube, look up the talk there and watch this. Similar thing for the object monitor stuff. So object monitors are used as soon as a feature is needed that is not supported by the lightweight locking. For example, when the lock is getting contended, or when somebody uses JNI for locking, or if somebody calls wait or notify on the lock, then the object is getting, we call it inflated to an object monitor, and the pointer in the mark word establishes the mapping between the object to the object monitor in the runtime. And this effort here, the object monitor mapping changes, are basically changing the way this association is done by using a side table. And instead of writing the pointer into the object header, we use the side table to track these mappings between objects and object monitors. There's a lot of things to talk about here. I'm not going into details about this. This is already lined up. I'm hoping for JDK 24. There's the bug report open and a PR ongoing under review. Right, and another thing that we did in Lilliput is a new, improved GC forwarding scheme. We call it sliding GC forwarding and self-forwarding. This is also basically the purpose of it is to not override the class pointer that is in the upper parts of the object headers. I talked about this last year, so you can look it up on YouTube and watch the details there. Finally, we were able to compress the class pointer, improve the class pointer compression to allow us to compress the class pointer to just 22 bits. I will talk about this later in a bit, because this also concerns the Lilliput 2 implementation. We have a JEP lined up, the JEP 450 compact object headers. I'm hoping we can make it into JDK 24, but no promises. I know that I talked about this last year, and I said, with good luck, we make it into 22. Didn't happen, so yeah. JDK24. The code is up there on the Lilliput repo if you want to try it. Yeah, and that's it about Lilliput 1. Let's go a bit deeper about what we call Lilliput 2. Lilliput 2 is basically the next step, making the object headers even smaller and save more memory. So basically what I talk about here is the tiny class pointers and compact identity hash code. So recap about the situation that we want to do. This is the current state in the JVM. We take 12 bytes for the header and the class pointer. Lilliput 1 shrink that to just 8 bytes, and with Lilliput 2 we want to make this even smaller and only take 4 bytes for all of this. So how does that work? The plan. So this is how we want it to look like. We still have the lowest bits more or less the same. We still have the log bits in the lowest 2 bits. We have the self-forwarded bits. We have 4 bits for the GCH. We have another 4 bits reserved for Valhalla. So far so good. And then we have only 2 bits for the identity hash code and only 19 bits for the compressed class pointer. How are we doing this? So there's two major topics here. One is about tiny class pointers. The other is compressed compact identity hash code. I want to talk about the tiny class pointers first. So what is terminology? First, we have a structure that is called class with capital K. This is intentional. This is the hotspot internal representation of a Java class. It has all the information that it needs. For example, instance layout, instance size, superclass, interface information, the OpenMap for the GC support, vtable, itable, etc. And the Java is basically the Java side counterpart is Java link class. This is also linked from there. What is the class pointer? So there is a special mode that you can use that's called uncompressed class pointers. It's basically what happens is that the class structure is allocated somewhere in metaspace. Quite simple. It requires 64 bits in the object layout. It allows for basically unlimited number of classes, except for whatever limits the operating system imposes. And you can activate this by passing this flag use compressed class pointers, minus use compressed class pointers, which is off by default, or basically, well, let's say this, it's a Boolean flag, right? So it's basically on by default, but it's you can turn it off if you want, but it's very rarely used. I made a survey across all the code at Amazon, and I found no single use of this flag. So the default in the current JVM is compressed class pointers. What it does is basically it allocates the class structures in a special memory block that is called class space. It only requires 32 bits in the object layout currently. It can address up to 4 gigabytes of class information, or about 4 million classes currently. Yeah, and it's on by default by this flag. The way it works is basically it's a relatively simple encoding and decoding scheme that is similar to compressed OOPS. So going from the actual pointer to this class, we subtract the base of the class space, and then we shift it because these class objects are allocated at 8-byte alignment. What we get by this is we have a contiguously filled class space, but the actual, let's say, narrow class pointers, we call this, you see those numbers there, which you see that the actual values are not very dense. There's a lot of like unused values by this. This is because it's not a class ID. It's really just a way to encode those class pointers. The idea behind the tiny class pointer encoding that we are after is because most classes, they are actually quite large. They are 512 to like 500 to about 1,000 bytes sized. Some classes are larger, most are smaller. This is what we found. So the idea is to increase the alignment of those class structures and increase the shift too, so that we can have much denser narrow class IDs here. So that means that the classes here, they are allocated at aligned to 1 kilobyte blocks basically, and we get almost a class ID for this. There may be cases like here where we have a class structure that is a bit larger, but it's not a big deal. We are losing just one value here, and it's very rare, so we don't have the 4 class ID in this case. Using this scheme, we can address about 4 million classes with 22 bits, which is what we have in Lilliput 1. With 19 bits, we can still address something like 500,000 classes. The problem with this, you can see this here, we now have holes in between those classes, which is basically just wasted memory. But we don't want to waste memory, we want to be efficient there. So what we can do here is, so each class structure has a lot of associated metadata in somewhere else. It's usually allocated in metaspace. In fact, the ratio between the space that is taken by the class structure itself and by the associated metadata is about 6 to 10 times, which means that we have up to 6 to 10 times as much metadata than we have actual class structure data. This is stuff like code caches, all sorts of extra information that is floating around. And a lot of this data is actually quite small, and we can be clever and allocate this in those spaces. So yeah, we don't have to waste those little blocks there, which is good enough. But the big question is 500,000 classes, is this enough? So if we shrink the addressable space there, and we can only address like 500,000 classes, is this good enough? So yeah, most workloads, they actually use much, much less than this. Most workloads use less than 10,000 classes, or maybe even a few 10,000 classes, often very much below 100,000 classes. Yet 500,000 classes might still not be enough. There's things like class generators, which generates classes on the fly or compile time. There's things like method handle and lambda forms that are generating classes under the hood. There's JRuby, which also generates classes. It's basically method handle lambda stuff. A lot more of these things. So yeah, there's ways to generate a lot more classes than 500,000. I've rarely seen this, but this is still, it's a concern. So we want to address this. So first shot of addressing this is that we have this insight that some categories of classes are never getting instantiated. So this is abstract classes, interfaces. I think some of the method handle stuff is never getting instantiated, but this is a question mark because I'm not sure about this. Which means that there's no instance error of those classes, which means that we don't have to encode those classes to begin with. There's no need to put them into class space. So this helps a bit. I think Thomas made some experiments and found that about 1/4 of all classes are just abstract classes and interfaces. If we can get some of the generated classes that is happening by method handles, lambda forms, and so on, or maybe JRuby, also fall into this bucket. A lot of this, our troubles basically could be solved by this. This is work in progress, but looks very promising. The other approach that we currently investigate, it's not implemented yet, but we have a plan basically that I want to line out, is a concept of far classes. What we want to, let's say the terminology first. So we call near classes whatever can be encoded with our 19 bits that we have. And we call far classes whatever is beyond that, whatever goes beyond those like 500,000 limit. We call far classes, and we need to find a way to address those somehow. And the way we want to do this, the idea is that for access classes that are basically beyond our addressable space, we write the full class pointer somewhere into this object. Basically, the only way to do this is we basically tack it onto the end of the object layout. And then we encode the offset to that field in this object layout in the object header. And by doing this, we enable basically an infinite number of classes. But it means that we have an extra indirection. We first need to read the object header. This points to the field where the class pointer sits, and then we can read the class pointer from there and end up at the class. But that's probably okay, because once we blow this limit of 500,000 classes, this is probably not our biggest concern anymore. And it should happen rarely, I think. Very rarely, actually. So how do we encode this in the object header? So the trivial, naive idea for this encoding is just grab one bit of this class pointer. This selects between near or far class encoding. The downside of it is this basically cuts our encodable space in half. We basically take one bit away, and we can only encode and address like 250,000 classes, which we don't really want, because on the other side, it means we would have a huge range for addressing those class pointers in the object, which we never need. So a better way to do this is by kind of overlaying the 19 bits a little bit. The scheme that we came up with is, let's say if you have 19 bits, and if the upper 8 bits of this are all zeros, if the upper 8 bits are non-zero, then we interpret all the 19 bits as a index into the class space, which we call near classes, which means that we must not allocate class instances at those points where those bits are zero. Because we want to, if the all the upper 8 bits are zero, then the lower 11 bits are interpreted as word offsets into the object. And this is where we find the actual class pointer that points to our class instance, the far classes. Yeah, and this means that we need to be careful where we allocate the class instances, but I think that's it's a problem that is not too difficult to solve. So yeah, we can encode far encoding. We can basically point to slots in the object layout that are as far away as 2084 words or 16 kilobytes, basically. Meaning we can do this for objects or for classes which instances are about 16 kilobyte large, which would be quite a lot of field. So write a class that takes this much space, good luck. It's probably generated or probably even very rare. So, but it's not, there's no limit, so we need to handle this. So what if instance size of a class is larger than that? In this case, if we have a class which instance size is larger than that, we basically insert the class slot at the earlier offset, basically at the last possible offset that it is, and lay out all the remaining fields around that. There's an extra gotcha here. What if we have a class A that is near encodable because it's still below this 500,000 or something plus limit, but it's already larger than this size of instance size that we could address a far class, and then we get a subclass B of that class A that is not near encodable. And we want to tag on this class pointer or insert it somewhere, but we don't have any space anymore because the instance size is already larger than this. So there's no slot for the class pointer there. The solution for this is that we have in mind is that any class that would exceed this instance size would get a class slot in it, regardless if it's near or far encodable. We need to reserve some space there in case we get a subclass that exceeds this size. Yeah, so far so good. Using this, we can basically have a much smaller class pointer, 19 bits, or we could even get smaller than this. So if we ever need bits in the object layout, we can shrink it to like 16 bits and get 3 bits more in the object headers, and still have like unlimited class pointer encoding. None of this is my ideas. So many thanks go out to Thomas Stüfer, who implement most of this stuff. John Rose and Colleen, who also experimented with it and came up with a lot of good ideas about this. With this, I want to change the topic a little bit and talk about compact identity hash code. Quick recap what this is about. So there's APIs in the Java-Lang system that's called identity hash code. It gives you a hash code for any object. And the contract here is that if you have two references and those are the same object, then the identity hash code must be the same too. This is very similar to the contract that you have in object hash code and object equals, except that equals is now the true identity of objects. The inverse is not necessarily true. So if you could just return like something like 42 for identity hash code and it would still be correct. Wouldn't be a very good hash code because it's what we want from a hash code is great entropy, and 42 is not that great. This also implies that the identity hash code must remain stable throughout the object lifetime. So if this must never change. Also notice that the system identity hash code is basically the default implementation for object hash code. But still, I'm talking about identity hash code and not object hash code. This is an important distinction. So the current situation for identity hash code is we allocate 31 bits, or we reserve 31 bits for the identity hash code in every object in the header. The first call to system identity hash code for an object basically generates a random number and puts it into this header slot that we have there. And any subsequent calls to identity hash code would simply basically read this from the object header and return that. A relatively small number of objects ever use this. So this is basically space that we allocate there that's rarely used. This depends a lot on the workload, actually. So some workloads make heavier uses of it. Most of workloads that I've seen rarely use identity hash code because they are good applications and they override object hash code with something sane. So how can we improve this? How can we not reserve 31 bits in the object header and do something better instead? So we have a naive idea here. This is basically what I've shown in my little demo at the beginning. We could take the address of an object and calculate a good hash code out of it and return that. Problem is that the GCs can move objects around, so the address changes over time. And this violates one of the contracts that we had, that the identity hash code must remain the same throughout the lifetime. So the next idea is here, could we allocate this slot for identity hash code on demand and only actually allocate the space when we need it and when system identity hash code is called? The problem is that the heap is filled contiguously and there's most likely there's simply no space at the end of the object. There may be some space if there's an alignment gap at end of objects, but in a general case, this is not possible. So what we came up with, or actually we didn't came up with that, is a suggestion that we got from people who already implemented this in different VMs, is we can have this identity hash code go in 3 different phases per object. So those phases are lined out here. So the first phase would be, no, we don't have any identity hash code. This is the default state that you get when you allocate the object. First call to system identity hash code would basically calculate a hash code based on the object address and update the state in the object. And then as long as the object doesn't move, recalculate this hash code from the address. And as soon as the object actually moves, we basically reserve a slot at the end of the new location of this object. Because now we can do this. When we move the object, we basically allocate a new block for this. And we can now allocate 1 extra slot for the hash code and stick the hash code there. And then every subsequent call would read from that. So this is the way we encode this in the object header. This is why we only need 2 bits here. So that we have the state of the meaning of these bits is if they are both 0, then it's the default state. There's no identity hash code. The first state is we called it at least once and it hasn't moved yet. And then we have the final state, which means there's the slot at the end of the object. Go look it up there. And a bit more in detail, the state transitions is basically exactly this. So it starts out with the default initial state. It's not identity hashed yet. As soon as identity hash code is called for the first times, we transition the state from 0 to 1, which means, yeah, we have called it at least once. And then we calculate the identity hash code based on the object address. And we keep doing this for every subsequent call until the next GC moves this object around. When that happens, we calculate the hash code based on the old object address for one last time, then make a copy of this object. We reserve an extra slot, if necessary, at the new location, and then we stick the hash code there. We update the state, we transition the state to this 1-0 final state, and from there on, we only ever read from that slot. So now, a common concern that I heard is, why is it even okay to grow objects during GC? Isn't that a problem when we could get the situation where like malicious or even by accident that we get increased heap usage after GC than we had before the GC, or even running out of memory during GC, or even worse, get a misbehaving GC. Why I think it's okay to grow objects during GC? So first of all, let's narrow down this problem a little bit. So I think legitimate out-of-memory situations because of excessive allocations, I think are okay. This is just a matter of fact. If you allocate too much stuff, you get an out-of-memory if you cannot deal with it. System identity hash code in this context is basically an legitimate allocations, in my opinion. Current implementation does this upfront. It basically allocates this slot for identity hash code upfront for all objects. The compact identity hash code implementation does it only on demand and in a deferred manner. So I think it's okay to throw out of memory if we cannot deal with this. What's not okay and what we need to handle is misbehaving GC. There must be ways to avoid misbehaving GCs. So I want to line out what basically give a very short overview about the different basic GC algorithms and why I think this is okay. So we have basically 4 different cases. We have a marked compact GC, which is basically a sliding GC that moves objects in place. It's used for parallel serial OGC and for G1 and Shenandoah full GC passes. We have 2-space like Scavenging GCs, which are the typical GCs that are used in serial parallel young GC and G1 young GC. And then we have region-based GCs like the G1 Shenandoah and ZGC, and we have kind of special case, but not really, concurrent GCs, Shenandoah and ZGC. So the most tricky like algorithm is the compact is the marked compact GC, which is basically a single space compaction, which is used as a old GC in serial and parallel, and also as a full GC in G1 and Shenandoah. The way it works is this is a very simplified view, but what we have here is a single space in memory. For this example, let's say we have those live objects here that are in pink, and we want to like compact them and get rid of those unreachable objects A, D, and F. The way it works is they are basically copied to the bottom of this memory block. It's basically sliding down, which is why I'm calling this sliding GCs. And we end up with object B in a location that was previously object A. We end up with object C sliding down on top of object B, and then we have object E sliding down to this. And then we have freed up space here, and this can be reclaimed. With compact identity hash code, we get the situation that we need to make space for hashed object. Let's consider again the same example. Let's say all those live objects have identity hash code, call them then. So we basically asking for making space for the identity hash code slot there. And okay, let's start from the bottom. We have object B, which is sliding down to the location of object A, and we see here that it's basically growing, and we tag on this extra slot for the identity hash code. It ends up being the same size as previously object A and B. And again, this is really schematic. It's not really useful, but it's good for reasoning about this problem. Next object, object C, that we have here is sliding on top of the object B, and it's not actually changing its location. You see that it's because object B has been grown, object C is not changing its location, which means that we don't have to extend this object. We don't have to, we must not expand this object, because otherwise we may trash over objects that are going behind this. So yeah, this remains the same. It doesn't grow. We also see that the state is not updated here. It's still 0, 1. It remains in this state. And then we have object E, which is sliding down to the location of object D, and it needs to be expanded to make space, and it's growing. If you think about this a little more, this has the interesting property that the overall usage of heap usage is guaranteed to not grow in this scenario. The worst case here is that the heap usage does not shrink, but this is already the case. There might be full GCs that don't yield any memory reclamation. So this is, it's basically okay. It doesn't misbehave. It still throws out of memory if it cannot reclaim any heap space, but that's the way it is. So two-space compaction works a bit differently. Two-space compaction basically has two spaces. This is why it's called two-space compaction. And we basically copy all the live objects from one space onto the bottom of the other space, which is empty. Which means we have, like, in this case, we have 4 live objects here, B, C, E, and F. And they are copied to the bottom of this other space here. And then when that's done, we can basically reclaim this complete space here, and that's it. With identity hash code, in this case, in this example here, what we get is, let's say we copy object B. They are all identity hashed, right? Those B, C, and E objects. Let's say we copy object B to the bottom of this 2 space here, expand it because it's changing its address. Then we copy C on top of this. We copy object E on top of this. And so far so good. But at some point, object F, we want to copy this on top of it. And it's no longer possible because we have actually grown in usage here. So this would result in like a GC misbehavior, and we must not do this. The way we deal with this is, so there's one thing. This is young GC. We have from and to space. They are equal sized usually. And then we have old space. And object can be promoted from young to old. And for objects that have their identity hash code called, we are promoting them straight to old space because we think that is the only way to deal with the situation. And it also makes sense because usually keys in hash maps tend to be longer lived than some other objects. So we promote them right away. And this way we guarantee that we don't run into this copying problem to 2 space here. We might still get a promotion failure. If old space is full and we cannot promote them to old space, we might still get the failure here. But this is already the case with current GCs. So they already deal with promotion failures by recovering from this and diving into Mark compact GC, which I have explained before is okay. So yeah, that should cover the 2-space compaction in my opinion. Then we have regional GCs, which is basically G1 and Shenandoah and ZGC. They are kind of similar to two-space compaction, except that they have more spaces. They have like regions which are smaller than the spaces, but they have more of them. And compaction works by basically doing the same thing, copying all those objects over to the other space. They have the additional advantage that if we run out of space in one region, then they can and they will simply pick the next region in their free set and continue copying there. So this is actually not a problem, in fact. So yeah, on overflow, pick the next region. This may still run out of memory, which I argue is okay. When that happens, they recover and dive into full GC, for example, in G1 and Shenandoah, and this is already all the case for current GCs. And the final situation with concurrent GCs, they don't really have the problem to begin with because allocations happen all the time during GC, and they can legitimately run out of memory anyway during GC. So the out of memory caused by the identity hash code expansion is really just a legit out of memory situation. And also the concurrent GCs are just regional GCs that I just described before. So I think this is okay. I'm open to discussions about this. I know you will. So putting this all together, we have tiny class pointers. They allow for only 19 bits for class pointers. We have identity hash code, which means we only take 2 bits of the object header for identity hash code. We also have an improved full GC forwarding table. I'm not going to talk about this here because I'm already running out of time. Yeah, and we keep reserving 4 bits for Valhalla because we are nice. Yeah, and by using this, we achieve like only 4 bytes for the object headers and nice memory savings there. You can get the code for Lilliput 2. This is already working in this repo. And yeah, I guess that's it. Oh, thank you.